again. Okay, let's have a ball, and this ball is moving along a table, and it is moving along at a certain speed. Okay, let's say maybe 2 meters per second. Now suppose it's moving along at the same speed for a few seconds. Then if I imagine plotting a graph of velocity against time, it's going to look something like this. Right, as the time goes, 1 second, 2 seconds, 3 seconds, and so on. That's the time in seconds. The velocity, which is in meters per second, would always be at 2 meters per second. All right, if the velocity has not changed, so every second is the same speed. And if I plot a graph of that, it is just going to be a horizontal line, the same speed. Now I'm interested to find the distance traveled by the ball. Let's say in 3 seconds. Okay, in 3 seconds, if I want to find the distance traveled by the ball, I'll talk about displacement. If I want to find a displacement, that's the displacement. Okay, I'll call the displacement x. Now we know how we can do that. All we need is to take velocity times time. Velocity times time gives me the displacement. And if we are talking about 3 seconds and 2 meters per second velocity, then it is simply 2 times 3. Velocity times time, and the answer is 6 meters. So we know how to do that. Now what is interesting is that we can actually find this from the graph. Let's have a look. The speed of 2 meters per second, if you look at the graph, it corresponds to this height here. Alright, and the time of 3 meters per second, it so happens that it corresponds to this horizontal length. So I'm multiplying a horizontal length by a vertical height. Now what does that suggest to us? It suggests to us that we are actually finding the area of this rectangle. Let me shade this area. You see, if I do 3 times 2, that gives me the area of this rectangle, which is 6. Okay, and so 6 meters, the 6 meters just happens to be the area under the velocity time graph. Now that seems simple enough just by looking at this picture. Let's see if we can push this idea a little bit further. Now in this case we have a graph in which the velocity is constant, right? Where this graph is just a horizontal line, and that's quite simple. We just get a simple rectangle for the area. But what if the velocity is changing? Let's think about an accelerating ball. Okay, all that. So this time, alright, this time, let me sketch the axis again. It's the v-axis and the time axis. Now this time, imagine a ball that is accelerating along a table. So let's start easy. Let's say in the beginning it's at rest, so 0 meters per second. And let's say after 1 second, let's think about what happens after each second. After 1 second, after 2 seconds, after 3 seconds. Okay. Now let's say the ball moves to here after 1 second. The ball moves to here, and then Okay, from here it goes to here, and then it goes faster and it covers a more distance, and then it goes even faster and comes here after 3 seconds. Okay, so suppose that after 1 second its speed has increased. Its speed has increased to, let's say, just make a simple number, maybe just, let's say, 2 meters per second. And after another second, increase to 4 meters per second, after another second to 6 meters per second. So it's accelerating. So we have this simple example. And if I want to plot a graph of this, I can do that. Now, in the beginning, at time 0, it starts from rest, so the velocity is 0 at the very start. After 1 second, now let me make some marks here. 1 second, that's 2 seconds, that's 3 seconds, and the time is in seconds. So, okay, I'll put some vertical scale. So let's say that's 2 meters per second, 3 meters per second, 4 meters per second, and 6 meters per second. And that's in meters per second. And then if I plot the points, it will be there for this time. And for the next time of 2 seconds, the point will be there, 4 meters per second. For this time, 3 seconds, it will be here. Okay. If I can then draw a straight line through that. And this is just a straight line. So that's simple enough for plotting the graph. Now, if I now want to find the distance, okay. What if I now want to find the distance covered during this 3 seconds? Now that's more tricky than before because the speed keeps increasing. I can't just take any of this speed. I can't take 2 or 4 or 6. I can't take any of this and multiply by the time. So what I have to do is a little bit more tricky. Now here's the idea. Let me just think of maybe just say a particular time. Let's say this time here. Okay, so at a particular point in time, it has a certain velocity. Okay, now let me think about what happens after a short time interval. After a very short time interval. Okay, I'll make an example. Let me say 0.1 second. Okay, so let's say at this time let's say the velocity here is 3 meters per second. So after a very short time interval, the speed increases a little bit, 3 point something meters per second. So, but if since the time interval is very short, we can imagine that the speed increase down here is quite small. So if I take the speed there to be roughly constant, then I can use the idea, the previous idea, of finding the speed, finding the distance by finding this area. So the speed during this short time is roughly constant. So we can imagine that, therefore, this area, this rectangle under the graph is roughly the distance traveled. Okay. Now, if we then consider another time interval, the next time interval here, where the speed is slightly bigger, we have a slightly bigger speed here, and then I can also find roughly the distance traveled by this same new rectangle. So it is as if we can find this the distance traveled by taking short periods of time, short intervals of time, and making all these little rectangles that keeps getting slightly taller and taller in this case. Okay, and if we make the time intervals small enough, it's quite accurate. Okay, and you can imagine doing that for the whole range of the 3 seconds using extremely small intervals, maybe a lot smaller than the 0.1 seconds. Alright, I have lots and lots of very narrow rectangles. Right, and each of these give me a little bit of the area that I want to find. And if I then imagine adding up all of the areas down here, right, adding up area of all of these rectangles, then surely I must get the distance that I want between 0 seconds and 3 seconds. So that's the idea. And what this idea tells us is that we can actually find the distance by finding the area under the graph. Now in this case, the area, if you look under the graph, is actually a triangle. Okay, let me draw this. It's actually this triangle that we are talking about. Okay, I'll just very roughly outline this triangle that I'm talking about. This is the one, this triangle here. So it's this triangle that we are talking about, and we can actually find this triangle quite easily. It's a simple shape. Okay, we know how to find the area of a triangle. Therefore, if I now want to find the distance traveled, or let me be more precise, I want to find the displacement. I want to find the displacement during this time, during 3 seconds. Okay, it's just the area. It's just the area under the graph. So the answer, therefore, since the area in this case is a triangle, is half base times height. Now the base is here, is the 3 seconds. So half times the base times, and the height, let's see, that's the height. It's 6 meters per second. So that's the height. Half times 3 times 6. And therefore the answer is 9. Right, the answer is 9. Units is in meters. So here we have just discovered a way to find the displacement of an object from the velocity time graph. And it's very simple. All we need is to find the area under the graph.